In this tutorial, we will discuss about ratios of transformer, that is voltage transformation ratio, current ratio and transformation ratio. We know that EMF induced in the primary winding of the transformer E1 is 4.44 F 5M N1. Likewise, the EMF induced in the secondary winding of transformer is 4.44 F 5M N2. If you divide E2 by E1, you will get, which is equal to 4.44 F 5M N2 divided by 4.44 F 5M N1. So cancel this, cancel frequency and flux. So E2 by E1 is equal to N2 by N1, which is equal to K. The ratio of secondary induced EMF to primary induced EMF is called as the voltage transformation ratio. K is called as the transformation ratio. So from this we can write E2 by E1 is equal to K, where K is equal to N2 by N1. So from this E2 is equal to K into E1. First case, if N2 is greater than N1, so number of turns in the secondary is greater than number of turns in the primary. So if N2 is greater than N1, the K obviously it will be greater than 1. So if K is greater than 1, then E2 will be greater than E1. So if E2 is greater than E1, it means the secondary induced EMF is greater than primary induced EMF. So this is called as the step up transformer. Second case, if N2 is less than N1, number of turns in the secondary is less than number of turns in the primary, then K will be less than 1, then E2 will be less than E1. So if the secondary induced EMF is less than primary induced EMF, it will be step down transformer. Third case, if number of turns in the secondary is equal to number of turns in the primary, then K will be 1. In that case, E2 will be equal to E1. So this is called as the isolation transformer or 1:1 transformer. Because the number of turns in the secondary and primary are equal, so that's why it's called as a 1:1 transformer. So the transformer can be a step up transformer or step down transformer or isolation transformer. Based on the number of turns in primary and secondary, the transformer will act as a step down or step up or isolation transformer. Now we'll see where step up, step down and isolation transformer are used in practical. At the generating station may be a thermal power plant or hydroelectric power plant where the electricity is generated. It will be in the range of 11 kV. We will not directly transmit this 11 kV because between the transmission and the generating station will have the transformer to increase the voltage. If you transmit the high voltage, that losses will be very less. So we'll have the step up transformer between generating station and the transmission. Here the 11 kV is raised to 440 kV. Then this 440 kV is transmitted over the transmission line. Then at the end of the transmission line, before the distribution, we'll have the step down transformer to lower this voltage to the 11 kV. Then this 11 kV will be distributed for utilization purpose. So the step-up transformer is mainly placed between the generating station and the transmission, and step-down transformer is mainly placed between the transmission and the distribution. Then we'll see what's the purpose of isolation transformer. Isolation transformer, also called as the 1:1 transformer. It won't change the output voltage. The input voltage and the output voltage will be same in case of isolation transformer. But what's the purpose of isolation transformer means? It will reduce the unwanted spike like this. If you pass the input signal with a spike to the isolation transformer, then the output of the isolation transformer will be like this. The spike will be reduced. And also this isolation transformer will not allow the DC component. So if any DC component present in the input voltage, that will be isolated, and only the pure AC voltage will be transferred to the next level. In this, V1 is the primary applied voltage, E1 is the induced voltage at the primary side, I1 is the primary current, and E2 is the secondary induced EMF, I2 is the secondary current, and V2 is the terminal voltage across the load. Next we will discuss about current ratio. For this we will assume that transformer is an ideal transformer. A transformer is said to be ideal if it satisfies the following properties. The first one is the ideal transformer has no losses. And the second one is ideal transformer winding has zero resistance. That means the resistance of the primary winding are zero, then the resistance of the secondary winding also zero. The third one is leakage flux is zero. That means 100% primary flux links with the secondary winding. So that means the leakage reactance is zero at the primary, and also the leakage reactance is zero at the secondary. So if you assume these three, then the ideal transformer has the primary applied voltage, that is V1 is equal to primary induced EMF E1, and secondary induced EMF E2 will be equal to terminal voltage across the load V2, because we are assuming that no losses. So we can write V1 equal to E1. So the primary input voltage will be equal to primary induced EMF. Then the voltage across the load will be equal to the secondary induced EMF. V2 is equal to E2. So already we derived E2 by E1 is equal to N2 by N1 is equal to K. So for instead of E2 by E1 you can put, so E2 by E1 is equal to, E2 is equal to V2 and E1 is equal to V1 in ideal transformer, so equal to K. Ideal transformer has no losses, so the product of primary applied voltage and primary current will be equal to the product of secondary terminal voltage and secondary current. So from this we can write V2 by V1 is equal to I1 by I2. So V2 by V1 is equal to I1 by I2 is equal to K. That is the current transformation ratio. So I1 by I2 is the current transformation ratio. So finally we can write E2 by E1 is equal to N2 by N1 is equal to V2 by V1, which is equal to I1 by I2, which is equal to K. Here one thing we have to observe, the current transformation ratio is reciprocal of voltage transformation ratio. Thanks for watching this video. Please subscribe for more videos. Thank you.